Hello everybody. In today's video we're going to go over trigonometry basics. These are all of the things you should have learned in geometry class during your trig unit in geometry. And so we're just going to go ahead and touch on the basics just to make sure that we have them down. Alright, so first of all, what are trig ratios? Trig ratios are simply a combination of the sides that we have on a triangle. So a trig ratio is going to depend on the angle that we're referencing, and then it's going to depend on which trig ratio we're using on essentially what our numbers are going to be. So let's kind of look into this and then you'll see what I'm talking about. So first of all, we have three sides to a triangle, right? Our hypotenuse is always going to be the side across from the right angle. So if we look here, we have our right angle right here. Our hypotenuse is going to be the side across from our right angle. It's also always going to be the longest side of our triangle. Now, what I would recommend is always locating the hypotenuse first, because it's never going to change, right? We always have a right angle. We're always going to have our hypotenuse. So always find the hypotenuse first. That's the easiest way to go. Now our opposite side is going to be the side across from our angle. Now in this case, we've designated that we're finding this angle here, which we've located with this, we call this symbol theta, and this usually represents our variable for our angles. So if we're using this angle here, if we're finding theta, our opposite side is going to be the one across from theta, which is going to be this right-hand leg here, right? So our opposite would be this blue leg here. And then our adjacent is the final side. It's also the side that's next to theta that isn't the hypotenuse, right? Because our hypotenuse and our adjacent here are both next to theta, but our adjacent side is the one that's not the hypotenuse. So our adjacent would be this bottom side here, all right? Now we're going to need to know the hypotenuse, the opposite, and the adjacent based on our angle in order to use our trigonometric ratio. So it's important to know which is which. So like I said, always start with hypotenuse, then find opposite, then find adjacent. And that'll be a pretty simple way to get where you're going. All right, so now let's talk about SOHCAHTOA. SOHCAHTOA is a easy to use guide that kind of tells you which trigonometric ratio uses which pieces. So here you'll notice that we have the SO, CA, and TOA. SO is a reference to our sine value, CA is a reference to cosine, and TOA is a reference to tangent. All right, and each of these means something different, right? You'll notice that we have our hypotenuse, our opposite, and our adjacent, and each of these are made up of opposite, adjacent, and hypotenuse pieces. So in other words, our sine of theta, sine, SO, SOH, is opposite over hypotenuse. Cosine, CAH, is adjacent over hypotenuse, and TOA, which is our tangent, is opposite over adjacent. So this acronym helps us know which pieces we need when we're evaluating our trigonometric ratios. Speaking of which, let's go ahead and practice what this would look like, right? So like we've learned the theory behind how it works. Let's put it into practice. So evaluating trig ratios, we have our SOHCAHTOA here. If you need to write this out, then I would recommend doing so just to kind of get a feel for it, right? So the first thing we're going to find is our sine, cosine, and tangent of A. Now, just like before when we had theta, we need to locate our angle, right? In this case, we're referencing this angle here, which we're calling A. And we need to find our pieces. The easiest one to find first is always the hypotenuse. And the hypotenuse is the one across from our right angle. So in this case, our hypotenuse is this side, which is 13. Right? The next easy one to find is opposite. So if this is our angle here, right, we can go opposite our angle, and our opposite in this case would be our 5. And then our adjacent is our final piece, which is the one next to our angle that isn't the hypotenuse, right? It's the last one. So our adjacent here is going to be 12. So now let's use SOHCAHTOA to help us evaluate what our ratios should be for these. So let's start with sine A. So sine is going to be this first part, the SOH, right? So sine is opposite over hypotenuse, and that's what the EOH mean here. So our opposite is going to be 5, because we stated our opposite was 5. Our hypotenuse is 13. So the sine of A is the opposite of adjacent, or opposite over hypotenuse, which is 5 over 13. So let's do cosine A. Cosine, if we look over here, cosine is adjacent over hypotenuse. Our adjacent we said was 12. Our hypotenuse we said was 13. So the cosine of A is 12 over 13. And finally, we have tangent. Tangent is opposite over adjacent. Our opposite we said was 5. Our adjacent we said was 12. So our tangent of A is 5 over 12. All right, perfect. So now what we need to do is now we're going to find the same thing, but we're going to find it with reference to angle B. So I'm going to erase these little things that we did here before, just to kind of reset it to where it was. And now what I would like for you to do is pause the video, and I want you guys to try to find B on your own, and then we'll get back into it together. So go ahead and pause the video and give it a shot. All right, so let's go ahead and give this a shot together then. Hopefully you guys got the same answers as us. All right, so first of all, we're referencing sine B, so we need to find our pieces, right? First of all, always the hypotenuse first. Hypotenuse is the one opposite our right angle. Our hypotenuse is always the same, right? This is 13. Now, our opposite in this case is opposite our angle B, which in this case is 12. So hopefully you saw that in this case, the opposite is actually 12 and not 5, right? And then the one adjacent to B, the one like right next to it here, is going to be our 5. So our 5 in this case is actually our adjacent. And you see how the trigonometric ratios change based on which angle we're referencing, right? So the sine of B is going to be our opposite over our hypotenuse. So this is going to be 12 over 13. All right. And then cosine of B is adjacent over hypotenuse. Adjacent was 5. Hypotenuse was 13. So our cosine is 5/13. And then our tangent of B is opposite over adjacent. Our opposite was 12. Our adjacent was 5. So tangent of B, opposite over adjacent, 12 over 5. That is our tangent. Now, there's some cool things to notice here, right? You'll notice that if we're referencing the same triangle, our cosine of A and our sine of B are always the same. And then our cosine of B and sine A are always the same. And then what's also interesting is that tangent A and tangent B are reciprocals of each other, which is kind of neat. Just a nice, useful tool if you want to remember that going forward. It's just kind of helpful in trig. So, all right, awesome. So that's how we use trigonometric ratios just on a basic level, just understanding what these trigonometric ratios are and how we can evaluate them. All right, so now let's try to focus on finding missing sides. So let's say we have a triangle. We know one of our angles, we know one of our sides, and we're trying to find one of our missing sides. So what we can do is we can find this missing side using the trigonometric ratios we used before, right? Now, remember the first thing we have to do is we have to figure out which angle we're referencing. So in this case, this might be one of those situations where just jumping into a problem may be actually the best way to go about it. So let's start off by understanding, well, first of all, we're referencing this angle here, right? We know that 19 is our hypotenuse because it's across from our right triangle here. It's across from our right angle. And we know that this x value, the other piece that we're looking for, is across from our angle. So our x is our opposite. Now, the reason why we evaluate which pieces we know, we don't have anything down here, right? And that's fine. We don't need it, right? We have our opposite. We have our hypotenuse. If we just quickly write out SOHCAHTOA, right? We have our hypotenuse and our opposite, which means we're going to use sine, right? And we know we're using sine because of the pieces we have. We don't have an adjacent, right? We don't know what the adjacent is, so we can't use this and we can't use this, right? So we use our sine. So let's do it just like we did before, but last time we did sine of A, right? That's because we didn't know our angle. In this case, we know our angle is 28 degrees. So what we're going to do is we're going to evaluate this as sine of 28 degrees, and this is going to equal our opposite over our hypotenuse. Our opposite was x, our hypotenuse was 19, right? So we can set this up like this. We can say the sine, and remember how we found that because we figured out we have the opposite and the hypotenuse. The sine of 28, which is our degrees, which is our angle measure here, equals x, our opposite, over 19, our hypotenuse. And now we have to solve for x. So in order to solve for x, we have to get rid of this denominator. So I'm going to multiply both sides by 19, multiply this by 19. And now we can put this into our calculator because we're going to have x equals 19 times the sine of 28 degrees. And we can put that into our calculator. So let's go here. So we have 19 times sine of 28. And always make sure you're in degree mode for these problems, right? Unless you're, for these specifically, we're just going to be using degrees. So we have 8.91. So let's go back. 8.91 is our x, which is this side here. So 8.91 is this side right here. That's the length of that side. All right, so for this next one, let's go ahead and try and pause the video, see if you can figure it out, see what you can figure out. If you can't figure out all of it, that's fine. We're gonna go do it together here in a second, but go ahead and pause the video and we'll get back into it together. All right, so let's give it a shot. So in this case, we have to identify which trigonometric ratio we're using first, right? So we have TOA, and I would get in the habit of doing this until you don't need it anymore, right? Just kind of write this out. So let's start off by figuring out which angle we are referencing. In this case, we're referencing this 55-degree angle, right? We know, first of all, well, what's our hypotenuse? Well, the hypotenuse is the one we actually don't know, right? In this case, it's over here. We don't have any information on our hypotenuse, so we're not using our hypotenuse in this problem. But we can find that opposite our 55-degree angle is x, so this is our opposite. And then the one that's not the hypotenuse that's next to it is this 8, so our 8 is our adjacent. So we have opposite and we have adjacent, which means we are going to use tangent. All right, perfect. So let's go ahead and set up our equation just like we did before. So we know this time we're using tangent. We know our angle is 55 degrees. So the tangent of 55 degrees equals our opposite over our adjacent. Our opposite is x. Our adjacent is 8. And now we can solve for x. So we have to multiply both sides by 8 to get x by itself. Multiply by 8, and we're going to get x equals 8 times tangent of 55 degrees. And let's get out our calculator. So now we have 8 times tangent of 55, and we get 11.4. So if we go back here, in this case, we know x is 11.4. All right, awesome. So we found the missing side, and that's all you're ever going to do for missing sides. You're going to evaluate to find, well, first you're going to identify your parts. You're going to figure out which trigonometric ratio you're using, and then you're going to fill in your equation, and then you're going to solve for x just using algebra. All right, so what happens if you don't know the angle, okay? So before, we were missing sides, right? Our x here was a side, x here was a side. You notice in this case, our x is an angle. Well, we're gonna have to do something a little bit different if we're finding the angle, but the beginning steps are very similar, okay? So first we need to figure out which one we need. So I'll do this for the last time here, okay? We'll write SOHCAHTOA, and then you guys can try it in the next one. All right, so we have SOHCAHTOA. Now, we're referencing this angle. Let's figure out which pieces we have. First of all, across from our right triangle, or across from our right angle here is our hypotenuse, which is 11. Okay, so far so good. Now, across from our x value is our opposite, but we don't have that, so we don't need that. And then our 8 is going to be our adjacent. So we have our hypotenuse and we have our adjacent. So in this case, we're going to use cosine because we have adjacent and hypotenuse. So let's set up the equation just like we did before, right? But it's just going to look a little bit different because of where our x is. So in this case, we're using cosine, right? And we don't know the angle measure. So we're going to say the cosine of x degrees equals adjacent over hypotenuse. Our adjacent is 8. Our hypotenuse is 11. So we're going to say cosine of x equals 8 over 11. Now, we're solving for x just like we did before, right? Now, when you use algebra, a lot of times what you're doing is in order to get x by itself, you're negating the other things around it, right? By taking the inverse. So if we think of cosine as being a function that we're using to evaluate x, what we can do is we can actually take what is known as the inverse of cosine, also known as arc cosine. There's a couple different names for it. But if we use this of x, right, we can actually take this of our value. So we can actually take the inverse cosine of 8 over 11. And essentially, if you really want to know the details behind what you're doing, right, you're doing the inverse cosine of x, right? And the inverse of something is just going to cancel all of this out, right? And that's going to equal, well, we took the inverse cosine of this side, so we have to take the inverse cosine of this side, right, of 8 over 11. So this is the actual algebra behind it, if you're curious as to how all this works. But essentially in your calculator, you're going to put the inverse cosine of 8 over 11, right? So if we go back to our scientific calculator here, clear this out. When you go to cosine here, you'll have to use your second feature, usually on your calculator. You have to use your second feature. So function here, if you click on function, it's this negative cosine sign, right? And then we have 8 over 11. So let's go back to our numbers here, 8 over 11. And you'll notice that we get, make sure it's in degree mode. This is very important. Whoops, didn't mean to do that. 8 over 11 is 43.34. So that is our angle measure, 43.34. So x equals 43.34 degrees, because it's an angle measure. All right, awesome. So go ahead and try that on the next one. We'll see how you do. Get as far as you can, and we'll go into it together. All right, so let's go and give it a shot. So we have our angle here. We're referencing this angle. We have our hypotenuse, and we have our opposite. So if we have hypotenuse and opposite, you can look back, you can write SOHCAHTOA if you want to. Hopefully you figured out we are using the sine function in this case. So we are going to say the sine of our x value equals our opposite, which is 10, over our hypotenuse, which is 19. And now in order to get rid of the sine, we have to take the inverse of sine of both sides. So the inverse sine of 10 over 19 is going to equal x. And now we can put that in our calculator. So 10 over 19 10 divided by 19 gives us 31.76, let's say. All right, so that's it. So x equals 31.76. All right, that's it. Excellent. So now we know how to find missing sides, right? We use the trigonometric ratio. We find the right one. We plug in our equation, and then we solve for x. And then missing angles requires us to use the inverse of our different trigonometric ratios, and we solve for our angles that way. All right, so now let's start talking about special right triangles. So the first set of special triangles we're going to talk about are known as 45, 45, 90 triangles, and these are essentially isosceles triangles with angles. They're isosceles right triangles, and the only way that's possible, if you have a 90-degree angle and the other two angles have to be the same, the other two angles have to be 45, right? Because 45 plus 45 plus 90 is 180, and all of the angles have to add up to 180. So let's do a quick proof so I can show you why 45, 45, 90 triangles work in the first place. All right, so we have the Pythagorean theorem, which we know is a squared plus b squared equals c squared. And let's assume that we have, just for the sake of it, let's assume that both of our sides, right, in an isosceles triangle, both of the sides are equivalent because the angles are equivalent. So let's say that we have side length x in this case. Let's just say that they're x. So if that's the case, we're going to have x squared plus x squared equals c squared, right? Which means we have 2x squared equals c squared. So when we take the square root of both sides, we'll get c equals x times the square root of 2, because the square root the 2 will stay in the square root, and then the x will come out because it's squared, right? So c will be x times the square root of 2. In other words, no matter what our side length is, our hypotenuse length is going to be that length times the square root of 2. So if we want to take this and put it into a form that we can use for problems going forward, if we have our legs, which I always define little legs as this like little l, little leg means little l, our hypotenuse equals our little length, our little l, times the square root of 2. All right, and we can use that to solve problems. We can go back and forth, we can go one way or the other. So let's go ahead and use this to solve problems. Remember, we can use this as an equation, right? Our hypotenuse equals our leg times the square root of 2, and then our legs are just whatever the legs are. We can go back and forth using that. All right, and let me show you how to do this. So let's solve for x and y. First of all, we should identify all of our angles and identify all of our pieces. It's a good idea to start with this the first few times you do problems. So we know that this angle is also 45 degrees, right? We need to make sure we have the special right triangle that we can use anyway. So we have a 45, 45, 90, so we're good. So x in this case is going to be our hypotenuse, and y and 25, these are both our little legs. And remember, the little legs are going to be the same. So this actually helps pretty easy, right? Because we know that if L equals 25, and if we know that y equals L, right, Who can tell me what this is called? There's a property where if A equals B and B equals C, then A equals C. Special points if you get that one right. So we have y equals 25. All right, so we solved for y pretty easily, right? So now let's jump into finding our x. Now, this is where it gets a little bit more tricky, right? But it's not too bad. Remember that our hypotenuse equals the little leg times the square root of 2. Well, what did we say the little leg equals? We said the little leg equals 25. So our hypotenuse equals 25 times the square root of 2. And that's our answer, right? We can't really simplify this much more than this. So x equals 25 times the square root of 2. All right. And just as a little hint to before, that property was called the transitive property. So in case you wanted to know if you got it right. All right. So what I want you guys to do is the next one's a little bit trickier, right? You're going to have to use this formula to help you solve for it, right? Because you're going to notice we don't have a leg at the beginning. Go ahead and try it and see how far you get, and then pause the video and we'll give it a shot together. All right, so let's go and jump into this. So first of all, identify our parts. All right, we have 45 degrees here. Now, you'll notice that in this case, we have the hypotenuse at the beginning, right? Our hypotenuse is 19, y equals a little leg, x equals a little leg. They didn't really give us any easy little legs like they did last time. And you'll notice that that's going to be a theme behind all of these problems, that we need to find the little leg first in order to be able to find all of our other parts. Even when we get into the next set of triangles, 45, 45, 90, 30, 60, 90, all of these problems you're going to want to find the little leg first. So if all we have is the hypotenuse, we're going to have to convert hypotenuse into little leg, and then we can find the rest, which in this case, they're the same. So you're going to just have one thing. So let's use our formula, right? Our formula here is that our hypotenuse equals our little leg times the square root of 2. Now, what do we know in this case? We know the hypotenuse equals 19. So let's plug 19 in for our hypotenuse. So 19 equals the little leg times the square root of 2. And remember, we're trying to solve for the little leg. So if we want to get the little leg by itself, we're going to divide by the square root of 2, divide by the square root of 2. And what we'll get is we'll get the little leg equals 19 over the square root of 2. Now, this violates a very important rule. You're not allowed to have a radical in the denominator. So if you have a radical in the denominator and it's just a monomial here, which means it has a single term, right? We can multiply the top and bottom by the square root of 2. This is a process known as rationalizing. And what this will do is, because we have a square root of a number times the square root of the same number, these square roots will kind of eliminate themselves, right? If you want to know the real math behind it, the square root of 2 times the square root of 2 equals the square root of 4, right? And then the square root of 4 just equals 2. So you'll notice that when you multiply the number, these two sort of things just kind of cancel out and it leads to the number itself. So that's what we're going to do over here, right? So we have 19 times the square root of 2. That's just 19 times the square root of 2, right? You can't multiply numbers inside and outside of a radical. And then over, well, square root of 2 times the square root of 2, as we showed over here, is just 2. So this is our answer, right? This is our little leg, which means this is also x and y. So x and y are both 19 times the square root of 2 over 2. All right, excellent. So let's go ahead and jump into the next one. All right, so 30, 60, 90 triangles. Now these are they're very similar to the last to 45, 45, 90 triangles. They just have a little few extra rules, so you have to kind of convert between them, and just be careful when you're looking at like evaluating which piece is which. All right, but it works in kind of the same way, where you're going to use a formula to solve for the little leg, and then use that to find other things. So let's go and jump into this. So first of all, to find the proof, to show you why this works, right? If you don't care about the proof, I would recommend strongly considering watching this part. But if you don't really care about the proof, go and jump down here, and we'll get into that and get into some problems. But the reason why it's important to understand the proof is because it helps you understand why these pieces make sense. So first of all, and this is going to sound a little strange, but let's start off with an equilateral triangle, okay? And for the sake of this, I'm going to say that each of these sides equals 2x, right? So we're going to start off by saying that each of the sides of the equilateral triangle are 2x, and then of course each of the measurements of the degrees on the inside are all 60, right? That's what an equilateral triangle is. So Let's go ahead and take this triangle and blow it up a little bit. I have it here. I labeled the angles A, C, and B, which gives us the side lengths AB, BC, and CA. And of course, all of our pieces here are 2x. And then you'll notice what I did is I took a bisector, and let's just grant me, for the sake of this, I could go into more details as to how this works specifically, but just grant me for now that I am bisecting this angle, and I'm also creating a midpoint from C to B. So CD equals DB. In other words, if this length was 2x, I'm cutting this in half, making CD x and making DB x. So I'm basically just taking this line, this altitude, and I'm breaking up this bottom piece into 2 equal parts. Now, what that's also going to do is, because it bisects this angle, both of these pieces are going to be 30 degrees. Because remember, this was once all 60, so now each of these are 30. So we have a 60-degree angle, a 30-degree angle, and a 90-degree angle, and we have 2 of these triangles kind of combine into the whole thing we had before. You'll also notice that now, if we just take a look at one of these right angles, let's look at one on the side here, we have 30, 60, 90 triangle. Our hypotenuse is 2x, and we have a leg. This leg across from our 30-degree angle, right, is x, and we don't know this leg here. So we don't know the length of this here, AD. We don't know this length, right? That's the length we're trying to find. So let's use the Pythagorean theorem using 2x and x to solve for this. So if we have x squared, right? We have to square this value, plus AD squared, right? This other leg, equals the quantity 2x squared, right? What we can do is first, let's actually distribute this exponent. So we'll have 4, right? Because 2 squared and x squared. So 4x squared equals x squared plus AD squared. Let's subtract x squared from both sides. That'll give us AD squared equals 3x squared. Now we can take the square root of both sides, right? I'm going through this kind of quick, but just trust me on the algebra here. You take the square root of both sides, you're going to get AD equals x times the square root of 3. Technically like plus or minus, but we're talking about distances, so it's always positive. So AD equals x times the square root of 3. And so what we can do is, if we want to kind of use this to generalize as a rule, what we've learned is that our legs here, right? If we have this 30-degree angle, let's start here, right? 30 degrees. Across from the 30-degree angle, you'll notice this is the smallest angle. It's going to create the smallest side. So on a triangle, if you have 3 pieces, right? Let's make these all different sizes. I know this is a bad drawing, but you're going to have an angle that's the smallest, right? So this angle here is the smallest angle. It's going to create the smallest side, right? We call that smallest side the little leg. Then you'll have a slightly bigger angle here, and the bigger angle is going to create a bigger leg, right? And then in our 90-degree triangle, our right triangle here, you're going to have a hypotenuse, which we just call the hypotenuse, okay? So in our 30, 60, 90 triangle, that's what we're going to be using. Across from our 30-degree angle is our little leg. Across from our 60-degree angle is our long leg, which I use a capital L because it's a taller L, right? Long leg. And then we have our hypotenuse, which is across from our 90-degree angle, and that is going to be, well, it's our hypotenuse. Now, these are the equations that we figured out from before, right? We figured out that, okay, across from the 30 is x, which is what we're calling our leg, right? Across from the hypotenuse, if we look back up here, across from the hypotenuse is 2 times x, right? In other words, our hypotenuse is 2 times our leg. And then across from our 60 degrees, so across from our long leg, let's say, would be what we found for AD, which we found was x times the square root of 3. So it's going to be our little leg times the square root of 3. So this here, this little drawing that I've done here, contains all of the equations that we're going to need to help us solve anything we would run into with 30, 60, 90 triangles. All right, so let's go ahead and jump into solving a few problems here. So we have solved for x and y. We have a couple pieces missing. I'm going to try to piece this so you can still see up here a little bit. All right, so let's solve for x and y. First of all, identify your parts, right? That's always a good idea. So here is going to be my 30-degree angle, right? This is our 60-degree and our 90-degree. So we know 30 degrees is going to be down here. So this is going to be our little leg. We know 60 degrees is going to be over here. So this is our big leg. and then our hypotenuse is going to be over here, so y is our hypotenuse. Okay, the reason that's important is because we need to figure out which piece we actually know, right? We don't know our long leg, because that's just x, and we don't know our hypotenuse, because that's y, but we do know that our little leg is 5. And like I said, a good first step is always to find the little leg. So if they give you the little leg to begin with, your problem is going to be very simple, right? So if we know that the little leg equals 5, right? Let's solve for the big leg first. We know that the big leg equals the little leg times the square root of 3. Well, if that's the case, we know our little leg is 5, so let's plug that in. We have big leg equals 5 times the square root of 3. And like I said before, you can't multiply numbers outside of and inside of the radical, so this is your answer, right? The big leg is 5 times the square root of 3, and then remember the big leg was x, so that's our x value. So now let's find y, right? And again, if we have the little leg, this becomes pretty simple, right? Our hypotenuse, we know, equals 2 times the little leg, right? If you need to reference up here, right? It's up here. Our hypotenuse equals 2 times the little leg, and our little leg was 5. So we're going to plug that in. So our hypotenuse equals 2 times 5. A little bit of very complicated math later. We know that our hypotenuse equals 10, right? And our 10 was our hypotenuse, which was y. So that's it. We know that x is this, right? 5 times the square root of 3, and y is 10. All right, so we used our special 30, 60, 90 triangle, identified some parts, found the long leg, the little leg, and then the hypotenuse. And once we knew that we had the little leg at the beginning, we kind of just plugged the stuff in, and it made it a little bit easier. All right, so now let's do one more. Go ahead and pause the video and give it a shot. Remember to identify your parts. Get as far as you can. You'll notice that in this one, they didn't give us the little leg right away. So it's going to be a little bit more difficult, but we can do it. So give it a shot, pause the video, and we'll get into it. All right, so let's go and give it a shot. So first of all, identify our parts. We know this is the 30 degree because they gave us the 60. So let's identify our y is going to be our little leg. Our x is going to be our long leg. And then our 16 is our hypotenuse. So in this case, they gave us the hypotenuse, right? That's the piece we know. So that's where we're going to have to start. We're going to have to start with that hypotenuse equation. So if you got this far, if you identified the parts, that's good, right? This is the step that we got to use to get started though. So we know that our hypotenuse equals 2 times the little leg, right? That's our formula. Now, what piece of this do we know? We know the hypotenuse equals 16. So we can plug that in. So 16 equals 2 times the little leg. We're solving for the little leg, right? That's what we're trying to find. So divide by 2, and you'll get that the little leg equals 8, which makes sense, right? It's half of the hypotenuse. So our little leg equals 8. So we know that y equals 8. Okay, we found one of our answers. Now that we have the little leg, we want to use the little leg to find the big leg, right? So if you knew the big leg to begin with, use the big leg to find the little leg, and then the little leg to find the hypotenuse. Because we knew the hypotenuse, we're going to use the hypotenuse to find the little leg, use the little leg to find the big leg. Always find the little leg first, okay? That is always what we're going to do. So now let's find the big leg. So we know that the big leg equals the little leg times the square root of 3. That's our rule here. So we also know the little leg equals 8. We solved for that, right? We figured that out. So we can say the big leg equals 8 times the square root of 3. And that's it. That's the answer, right? There's nothing more you can do with that. We'll say that that equals x. And that's it. That's the problem. All right. Well, I mean, if we back up and take a look at this, we've done a lot of work, right? This is all the stuff that you learned in trigonometry. Now, if you want to get a little bit more complex into some of the stuff you could have learned angle of elevation, you could have learned angle of depression, you could have found geometric mean. There's a couple other topics you could have learned. But as far as understanding what you need for Algebra 2 trig, this is a really good first step. So yeah, if you have any questions, come see me, and I will see you guys in the next video.